Alright, let's do some exercises about rings. So, we're gonna pretty much all our rings from now on, well, I guess from now on isn't like since this is the first exercise we're doing, but all of our rings are going to be commutative because commutative rings are ones where you can say a lot of interesting things. Anyways, let this fancy n be the nil radical of a. Is nil radical okay, so maybe it is one word. But anyway, so this is the set of all nilpotent elements, i.e. the set of all elements a and a, such that a to the n is 0 for some natural number n. Of course, not including 0, because I'm an analyst, blah, blah, blah. You've heard me rant about this before. Prove that n is that the nil radical is the intersection of all prime ideals. So in order to do this, this is sort of there's a lemma that you have to prove here, and let's see here. I know I've seen this problem done one time where they actually that you prove this lemma in a previous problem, and then they ask you to prove this statement. So if you're just given this problem, it's not immediately obvious that this lemma is useful, but if you've seen it before, then you know to use it. So it sort of goes back to that whole thing about, like, I feel like there's a lot of algebra problems where it's just like, okay, so how do we know how to solve this problem? Oh, well, of course, you know how to solve this problem because you've already seen the solution before. So it doesn't make sense. There's a lot of times where you use things in algebraic arguments that I think aren't very, like, it's not obvious that you should use that. But anyways, if you sort of know what's up with ring theory, then you know that this lemma is going to be useful. So anyways, suppose we have a non-empty set S, just any subset of A, which does not contain 0 and which is closed under multiplication, and let P be a maximal element of the set of ideals of A whose intersection with S is empty. Certainly such a maximal element exists because, let's see here. Well, we need to prove that there is such a thing. Okay, so we do that. Okay, so I claim that P is prime. So to prove this, first note that such an ideal P exists since the zero ideal is such an ideal. Right, because the zero ideal is an ideal, and since S does not contain 0, S does not intersect with P at all. And so there is such a thing, and so there is such an element in the set of ideals whose intersection with S is empty. And of course, we have a maximal element because I think you would have to go through, like, you might have to go through another Zorn's lemma argument here. You take this the set of ideals whose intersection with S is empty, and you give it a partial order by inclusion, and then you prove that every chain has a maximal element, namely the union, and therefore there is a maximal element with respect to inclusion, and this maximal element ends up being a maximal ideal of the set of ideals whose intersection with S is empty. Okay, so we know that such a thing exists. Now to prove it's prime, well, okay, hold on. Now I'm thinking about this because maximal ideals are... Okay, right. So just because it's a maximal ideal, it's right. It's a maximal ideal, or it's a maximal element in the set of ideals whose intersection with S is empty, but that doesn't necessarily mean it's a maximal ideal. And so we can't necessarily... We know that maximal ideals are prime, so we can't immediately say, oh, so P is going to be prime. We don't know that it's a maximal ideal, and so we have to prove directly that it's a prime ideal. Okay, so what we want to prove is that if the product AB is in P, then either A is in P or B is in P. You take the contrapositive of this, if both A and B are not in P, then we need to prove that the product is not in P. So suppose we have two elements which are not in P, and consider we're going to take two ideals. So the first one will be this fancy A, which will be the ideal generated by A and P. Then P is a proper subset of A, because certainly since A is generated by A and P, it contains everything in P, and it's proper because we have this element A which is in fancy A but not in fancy P. Alright, so we have a proper ideal, or we have an ideal which properly contains P. Similarly, if you let fancy B be the ideal generated by B and fancy P, then again fancy P is a proper, it's an ideal which is a proper subset of the ideal fancy B. Alright, so P is a maximal element of the set of ideals which intersect trivially with S. The fact that A and B contain P implies that A and B must both intersect non-trivially with S. In particular, there exist elements S sub A, which is in the intersection of A and S, and SB, which is in this intersection of B and S. So what does this mean? How can we write these elements of SA? Well, we know that elements in A are generated by A and P, and so therefore there must exist elements PA and PB, and RA and PA and PB in the prime ideal, and RA and RB in A, such that SA is A times RA plus PA. And that's because any element in the ideal generated by A and P, you can write it as, well, it's going to be sums or finite sums of multiples of elements in P plus multiples of A. And by multiples, I mean multiples with coefficients in the ring. So in particular, we can take A and multiply it by some R and then add just some combination of things in P, which again will itself be a thing in P, and so we can just take it to be a thing in P. And note that we're using commutativity here because for ideals you need to be closed under left and right multiplication by elements in the ring, but that's the same thing. We just move them all to the same side. Alright, so SA is equal to A, RA plus PA, and SB is equal to B, RB plus PB. So let's take AB, RA, RB. You use commutativity here, and then you substitute in these, let's see here, A times RA. So if we move the PA over, then this is SA minus PA, so that's how we get this, and we get this similarly. And then we just FOIL it out. We know S is closed under multiplication, so this term is in S. Now assume for contradiction that these that this sum here is in P. Then since P is an ideal, this term, and this term both contain elements of P as factors. And so then, since ideals are closed under multiplication and addition, well, all three of these things are in P, and so this the sum of these three terms is in P. Alright, so if this whole sum is in P, then what you can do is you can take the sum of these four things and write it as like equal to, let's say, P0, which is an element of P. And then you take these three terms and move them to the other side, and you get SASB. SA times SB is equal to a sum of elements of P, and therefore SASB is in P. But this contradicts the fact, because SASB is an element of S, this contradicts the fact that S intersected with P is empty. Therefore, it cannot be the case that this sum is in P, and therefore this term, this element, is not in P. Alright, so this is not in P. Since P is an ideal, if A and B were in P, then multiplying by RA or RB would keep us in P since it's an ideal, and therefore this would imply, and since this cannot happen, this cannot happen. So we have AB is not in P. So that's exactly what we've proven. Or that's exactly what we wanted. We wanted that if A and B are not in P, then A times B is not in P. Therefore, P is prime. Alright, so we've proven that if we take a non-empty subset which does not contain 0, then the maximal ideal whose intersection with S is the maximal ideal of the set of the maximal element of the set of ideals whose intersection with S is empty is a prime ideal. Alright, with this in mind, what were we trying to prove again? Oh yeah, the nil radical. The set of nilpotent elements is equal to the intersection of all prime ideals P. Okay, so let's prove that. Let P be the collection of all prime ideals of A. Did I introduce this well? So, yeah, I guess I could have wrote more details here. Let's see here. N is a set of nilpotent elements, but we have no idea. It's not entirely obvious at first. Oh no, it is. We've talked about this. I go over this in my lecture series that the nil radical is an ideal. So n is an ideal, and we want to prove that this ideal is equal to this ideal. And certainly this is an ideal because it's an intersection of ideals, and we know that ideals are closed under arbitrary intersections, actually. So to prove this equality, we're going to prove inclusion in both directions. Alright, so first let's prove that n is contained in the intersection. So let's take some element a and n. We want to prove that it's in the intersection. So we want to prove that it's in every single prime ideal P. So let n be a natural number such that a to the n equals 0, and let P be some prime ideal. Then a to the n equals 0, but 0 is in every prime ideal. Well, it's in every ideal, so it's in every prime ideal. Now, we know that by definition of a prime ideal, if A times B is in P, then A is in P or B is in P. This extends to finite products. So if you have A1 times all the way up through AN, my pen is like super sensitive right now. I don't know why. It's like, even if I'm like not touching the screen. Oh, now it's better. Okay, so if the product of A1 through AN is in P, then A1 or this pen is not working. I'm not even going to try. So basically, if you have a product of things A1 times A2 all the way up through times AN is an element of P, then some AI must be in P. And that's just a very easy induction argument from this statement. So therefore, if a to the n is in P, then one of the factors is in P. So either A or A or A or A, blah, 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 is in P. But that means A is in P. So one of the factors of AN is in P, and since A is the only factor of a to the n, A is in P. So therefore, so anything in n is in this prime ideal. And this holds for every prime ideal, and so then A is in the intersection of all prime ideals, and this holds for every A and n, and therefore n is contained in the intersection of all prime ideals. Alright. Now for the other direction, this one's a little trickier. Well, not trickier, just it's not quite as obvious how to go forward. So we want to prove that the intersection is contained in here. It turns out it's easier to prove that, like, A is contained in B if and only if B complement is contained in A complement. So we're going to prove that the complement of n is contained in the complement of the intersection. Okay, so suppose that we have an element R which is in this thing here. So R is not in n. And let S be the set of all powers of R. Then S is not empty because it contains R, and it's closed under multiplication because R to the m times R to the m is R to the n plus m, which is going to be just another thing in the set. Furthermore, R is not in the nil radical, so it cannot be the case that R to the n is 0 for any n. So since r to the n can never equal 0, 0 is not contained in S. So S is a set which does not contain 0 and which is closed under multiplication. Therefore, the lemma that we proved at the beginning applies, and so there exists a maximal ideal P of A which does not intersect S, and furthermore, this ideal is prime. So there is a prime ideal P such that the intersection of S with P is empty. So therefore, if the intersection of S and P is empty, R cannot be in P. Right, because if R were in P, then R would be in the intersection, contradicting emptiness of the intersection. Okay, so we found a prime ideal such that R is not contained in this prime ideal. But then certainly it can the more restrictive statement of R being in the intersection of all of these prime ideals cannot hold. So R is not in the intersection of all these prime ideals. And so every element which is not in N is also not in this intersection. Therefore, equivalently, every element in this complement is contained in this complement. And then equivalently, this thing is contained in this thing. The intersection is contained in the nil radical. So we have inclusion in both directions, and therefore we have the nil radical is equal to the intersection of all prime ideals. And that's exactly what we wanted to prove.